This is chapter 5. It's all about how to display and describe quantitative data. If you remember, chapter 4 was about qualitative data. So let me take you through multiple important topics of today in this handouts. So it's very important to understand that in decision making based on data, we get different types of data like qualitative or quantitative. And as you can see here, we have two types of data. We talked about that before. Qualitative data on the left hand side, we call it categorical as well, and numerical data on the right hand side, which is quantitative data. So categorical data, in fact, was the topic of chapter 4, while numerical data or quantitative is the topic of chapter 5. We're going to go through multiple slides to discuss how to present and the meaning of multiple metrics or statistics when it comes to numerical data. This could be an interesting slide to show you in a nutshell what kind of statistics we can get from our data. So if you look at the left hand side, we have graphical data, or in fact a graphical representation of our data. One dim, it means one dimension or one variable or one column in our spreadsheet, and obviously two dims, it means two dimensions if we want to make any relationship. Maybe you have noticed in chapter 4 we happen to look at the relationship between two variables, categorical variables, through contingency table or crosstab, or in fact what we call it in Excel pivot table. Today we're gonna look at the quantitative part, which is histogram and boxplot. You can see histogram, it looks like a column bar chart. We will come to it soon. And the box plot, you can see it here. It's a very small representation, but it could be horizontal like that, and sometimes we will see it vertical, and we will try to understand the difference. If we look at the scatter plot, this will be the topic for chapter 6 and chapter 7. If you look at the right hand side, on all these let us say metrics or statistics, which can be calculated definitely using software. We have central tendency of the data that can be measured through the mean, which is the arithmetic mean, or we call it average. Also, we can look at the center of the data through the median, the mode, and also mid-range. And mid-range is the average between minimum and maximum point, which could be a very good representation to the middle of the data, because we are always interested in the middle of data. So the mean could be good candidate, the median as well, the mode, which is the most frequent. Median is basically the middle of the data, exactly in the middle. That means 50% of the data will be less than this value, and 50% are more. When it comes to the mean, it's still in the center, but the center could be shifted and it could be in the middle exactly, and this will lead us to a concept called skewness. When it comes to variation, which is very important to understand that the center point is not enough, but also we need to look at the rest of the data, how the rest of the data are distributed or spreading around the center. So there are multiple index that gives us a little bit of information about how the data distributed. So variance is the most important component from which we can calculate the standard deviation. The range is basically the difference between minimum and maximum. When it comes to coefficient of variation, is sometimes I call it a combo in terms of combinations between two metrics, which is the standard deviation divided by the mean. So if you get the standard deviation of your data, which is the variation, divide by the center of the data, which is the mean, you got what we call it coefficient of variation. And sometimes we represent in percentage, and if the percentage is high, it means there is a very high risk if we are talking about stock. If the CV, in this case the coefficient of variation, is small, probably because of it's not really risky enough. When it comes to the shape of the data, we have two metrics here. One is called skewness and one is called kurtosis. We're gonna go and discuss about them soon. When it comes to position, we have multiple components here. The z-score. Z-score is the kind of standardization of the data, which is really very useful when it comes to comparison among different data that has either different scales or maybe different units. Percentile is basically a percentage of the data, so the location of the data. So sometimes if you want to know you got a grade for your exam and you want to know where your point is with respect to the rest of the class, whether you are in the highest 5% or 8% or 2% or in the lower 15%. So once started to look for percentage, is what we call percentile. Nevertheless, there are some standards like a 25 percentile, which is we call it Q1, which is the first quartile. Second quartile, which is Q2, which is basically the second quartile, which means 50 percentile of the data, which exactly the same value as the median. Q3 is the 75 percentile, which means 75% of the data are less than this value and 25 are more. IQR is basically the interquartile range, which is the difference between Q3 and Q1. So this is another representation, the IQR for the variation. I will not really go through basics here because probably you can read it as well as you can really remember from previous studies. So this is the variance, standard deviation, coefficient of variation, and range, as well as the interquartile range, which I just talked about them. Skewness is very essential method or metric that gives us a very important information without really drawing our data like histogram. But skewness could be a negative, it could be positive. So it's basically the shift in the shape of the distribution. So instead of having a normal distribution, which is symmetric, sometimes, and in symmetric distribution, we usually, the data will have two tails, one on the left and one on the right. And for not skewed data or for symmetric data, as the name should be, it means the two tails are equal. But in many cases, we don't get perfect symmetric of data. In this case, the data will be shifted because of certain reason, either by nature or by maybe malfunctionings, or maybe something happened in our environment or our process or in our operations that made the distribution to be skewed. So we need to understand if the skewness is not natural, it's not normal, then why we have skewness. If we get the skewness equal positive here, SK for skewness, which means the tail is on the right hand side. In this case, the mean is greater than the median, because symmetric data, mean and median are equal. And it means that there is a high probability for low values to happen and low probability for high values to happen. And this is example for waiting time and bounce rate from websites. This is the this is when it comes to the shape of skewness. If you can see here, it's on the upper or the top of this graph. This is basically skewness. When the tail is really longer on the right hand side, we call it, let me choose here, maybe like a laser here, Hopefully you can see it. So here you can see the tail is on the right hand side, so this is skewness to the positive skewness. Down here the tail is on the left, so it will have be a negative skewness. Okay, so let me get rid of this kurtosis. It means that if the red, the one in the middle is called normal distribution, and the kurtosis is 0. When the kurtosis is positive, we know that we'll have the distribution is a little bit squeezed in to the inner part. It's like you are pushing the tails from outside to inside, so you get peak like the red color distribution, which is the kurtosis here is positive, and the scientific name is called leptokurtic, which means positive. But if we have in the middle some flat distribution like this one, the one here is called platykurtic, which is like plateau or like flat. Usually it's the kurtosis is negative. So it's very important to understand the difference between negative and positive. And negative and positive, whether for skewness or kurtosis, doesn't mean always bad or good. It means actually negative and positive. But when we put the curve and the graph into context, like whether or not the distribution is data related to waiting time, related to grades of class, related to satisfaction, related to expenses, then we can make an interpretation for positive and negative, and we know later on which one is good and which one is bad. This maybe it's an interesting graph to show you the skewness and kurtosis. Skewness has negative and positive, as you can see from on the vertical, for the horizontal axis here. As for vertical axis, there is a negative and positive kurtosis. So, and in the middle you find 4 possible shapes based on the values of skewness and kurtosis. You can see when kurtosis is positive, you will see that's always the shape will be a little bit squeezed, as you can see in the top of this graph. But if you look at the negative kurtosis, you will see it a little bit. We call it a fat tail. It's a fat tail, and because but for kurtosis negative, you get a thin tail. This is, and the tail, whether left or right, this is the skewness task to tell us. If it's negative, it means the tail on the left. If it's positive, it means the tail is on the right. Okay, so z-score is how many, actually, not how many standard deviation. Let me see here. How many standard we have to go far from the center. So the z-score is just as you have seen in the previous slide. You take the value of that you want to calculate the z-score for, and you subtract from this value the average and the total divided by standard deviation. So if the z-score is 2, it means the value is 2 standard deviation far, but higher, because it's a positive 2. If it's a negative 2, it means the value is less than the average by 2 standard deviation. So that means the sign and the polarity of the z-score will be important. In front of you will see something called box plot with whiskers. And box plot, you can see it's like a box. If you let me get again here. So it's like a box here, and the lower bottom here, it's called first quartile, which is 25% of the data less than this value. There is a line somewhere inside the box here. It's called the median, or Q2 as well, or second quartile, as you can see on the left hand side here. And the third one on the top, it's called third quartile, which is the 25th percentile, as we discussed before. And the distance obviously is the IQR, or interquartile range. We use this IQR to calculate two levels here, or two fence, or two boundaries, or limits, or bounds, whatever. We use one's called lower fence and upper fence, and the lower fence is basically Q1 minus a part here, which is 1.5 multiplied by IQR. So if the distance is big, or the box is big, then the lower fence will be lower, very low, and the higher fence, or the upper fence, will be also high. So that means the lower and upper boundaries can be determined based on the size of the box. That's why we call it box plot. And these two fences, we call them whiskers. So in many cases, we use this box plot with whiskers. It's very important because any values or in our data are outside these two fences, whether lower and upper, we consider it as an outlier. And outliers is a very important topic. You cannot ignore it, you cannot remove it. You have to make sure that the outliers is real outlier in terms of error. If it's not error, you have to keep it in your data and to conduct your analysis with it. So outlier is very, very distracting, it's very disturbing, but also very important. So we need always to be careful, and we need to identify them. And this method in front of us is one of the methods to detect the outliers, as well as the previous slide, which talks about z-score. So z-score is another method to detect outliers. Okay, so now we go to the histogram. Histogram, it looks like a bar chart, but in a column format. And there is another thing, is called stem and leaf. And basically, stem and leaf is very old method. It's interesting to know about it. Not many software, it's probably no software nowadays use this this method, but this method was very old method where computer wasn't there, and there was no idea about the histogram. It was just handwritten things. That's why you see it's like handwritten. The idea is, in the past, people, when they collected data, that was handwritten, and they wanted to represent the data or summarize the data, so they came up with this method. It's called stem and leaf displays, which represent frequency distribution as well, which today we call it histogram, but it's represented not by the values, but represented by bar, as you can see on the left hand side and right hand side. So how stem and leaf works, let's go ahead here, take one example, this one here. So if you have a series of numbers, you need to sort them first in ascending format. That means the smaller one will start with, and we end up by the maximum. So once you put them like that, then you have to decide if you have two digits like this. So we take the left digit as a stem and the right digit as a leaf. So if we take it like that, so the 2, so in 20s we have 21, 22, 24. That's why we have 3 digits on the right hand side of this bar or line. 3, it's another one. We have how many numbers in the 30s? 33 twice, and 36 and 38. For that reason, we find here 3, 3, 6, 8. And finally, we have the 4. We have only one value, which is 1 here, which is 41. So basically, if you continue doing this, you will find out that this is kindly like a frequency, how many points we have in the 20s, how many points in the 30s, and so on. So it could be very useful in the past, maybe today is not. But because if you have big data or large data, you cannot do it like that, because otherwise it will be very disturbing visuals. You cannot really look at it. What would happen if you have 2, 5, or 300 values? You cannot write forever here, right? So it will be, because it has something like numbers, it's really very tough later on to visualize it. So it's not useful when you have large data, but you remember in the past there had no large data, because it was everything was collected manually. So, and it has every data should be recorded on paper or not booklet or whatever. In the end, today we have the histogram. What else here? Yeah, we talked about the shape. This shape histogram. It has two peaks, one on the left, one on the right. We call it here. Usually we expect only one peak. We call it unimodal. But when we have two here, we call it bimodal because it's two. But if we have more and more, then we call it multimodal. So multimodal, it means we have multiple peaks like this one. Usually we don't have more than two, but of course it depends on what are you studying. Normally we get one only, and in some cases two, and some other cases more. This is mostly, there's no one single peak. They are equal to each other more or less. And that's why we call it uniform distribution. It's very useful to understand the differences and so on. This is maybe on the left hand side, you can see one of the distribution, which we call it symmetric distribution, and usually the average or the mean and the median are on the same point, which is in the middle. And if you have symmetric data like that, you know immediately that the 50% of the data on the left and the 50% of the data are on the right. So this is when the data is symmetric. But usually, as I mentioned before, it could happen that the data might go in a different direction, like to be shifted like this. So you can look at this data is not symmetric anymore, and it's very obvious. It's the tail is on the right hand side, so the skewness will be positive. What does it mean? Basically, it means if we come here, this is the number of female cardiac patients. So, and this is how much they have been charged in money. So that means the majority here, this is good curve because the majority of female, they paid less than some others. So that's very important, and I think it's a good idea. It's a good information here. It's not bad. In that case, it's very important. So let me go to the next one to show you the left and right. You can see I tricked here. I put just a fictitious example, which is not in the handouts, but since you have this now, you can really understand what's going on here. It's imagine that we have two curves, one on the left hand side, we call it left skewed, and right hand side is right skewed, and imagine that they are representing grades. So on the left hand side, which is negative skewness, if the grade is always on the horizontal line, so grade ranges from 0 to 100. So it looks like most of the students here, which is in this case, let me take, this means that most of the students get higher grade, while on the right hand side here, you see most of the students get lower grade. So definitely the negative skewness in this case is better than positive skewness. Of course, if you change the variable from grade to maybe waiting time, then the right hand side would be better because it means most of the customer, they stay in the system shorter. But on the left hand side here, skewed to the left, it's really bad because it means most of the customers, they spend more time in the service provider. So it's very important to understand the shifts and so on. We talked about outliers, so I will not repeat myself. This is how we calculate the average. I think it's very obvious for you, and it's really not difficult. You just take the total and divide by this number of points. We know I talked about the median, and the median and the average are really nice to represent the data, but it's very important to see that the median is more more resistant to the outliers because it's a position. So you can imagine if you have outliers, average or the mean will change, sometimes dramatic, but the median will not change much. Sometimes it doesn't change at all. So it's very important to know which one from our statistics and metric will be sensitive to outliers. This is very important for you. I will leave it to you to read it and to understand the difference between geometric mean and arithmetic mean. The one that we have been talking about, it was arithmetic mean, which means you sum up and divide by number of points. Geometric means is different. It's very popular when for financial sector. So you need to know the difference, but most of the time we are using the arithmetic one. The spread, which means the variation around the center maybe, or the spread, it means how big the range in our data. So very simple method here. We take the maximum and minimum and take the range. This is another, it's the one that I talked about it. So maybe here more text. So it's good for you to understand the difference and so on. Variance and standard deviation. So variance, it's definitely extremely important when it comes to data analysis or decision making, because variance is the key for indicating if there is a risk, if there is no risk, or maybe there is consistency, there is reliability, or maybe not. So all of these things can be explained by the variance. So variance has to be first calculated. As you can see, we have two variants here, one for the sample, one for the population. If you remember from previous chapters, the sample variance, we call it statistics, while the population variance, we call it parameters. For that reason, the parameter we represent the variance or the parameter with Greek letters, but with some Latin letters like S, we use it to represent statistic. So you can see it's here the difference, but squared, because if you don't take the square, the summation will be 0 in the end, and you think maybe there is no variation while variation exists. So that's why squaring the difference became very essential, because it will not cancel the positive against the negative. We divide by something called n-1, or call it degree of freedom. It's a little bit advanced topic, so we'll not talk about it. Maybe you will hear about n-1 in other course, like advanced one. Standard deviation is basically you take the square root of the variance of the sample, you get the square root. Why square root is important? Because the variance, if you look at the equation of variance, if the raw data in Canadian dollar, the variance will be in dollar squared, which is really not physical currency. But if you take the square root of variance square, or the variance, you square root as well the unit. So in the end, you come up with the same unit, which is Canadian dollar, as the raw data, which is very useful for us. CV, as I mentioned, is a combo measures. You take the standard deviation divided by the mean, and you multiply by 100 to get a percentage. The higher the percentage, the risk will be higher. If the percentage is smaller with respect to other products, then you know that there is no much of risk. Let us shift some of the slides. This is also very important. Sometimes if we get we know from these slides, if we get the raw data and you want to calculate the average, you sum up all points in your sample, divide by the number of sample, and then you get the average. Sometimes we are not given the raw data, we are given summary data like this one here. So it's kind of processed data already. Basically, I call it even information. Why? Because it is not raw data at all. It's already aggregated data, but yet we need to calculate the average. But in this case, the average will be weighted average because we don't have the details of the data. And also, when we get the average, we need to calculate the variance as well as the standard deviation. Let us see. All what you need to do is to go through the process. After you get the range, you get what we call it the midpoint, because we need a point, because we're going to multiply, so we cannot multiply against range. So for each of these ranges on the left hand side here I'm going to get the midpoint. So the midpoint of 0 is 0, the midpoint from 1 to 5 is 3, from 6 to 10 is 8, from 11 to 19 we're going to choose 15. And anything else greater than 20, we're going to use 30 as a midpoint. But by the data that was given to us, We know that this range count for 23%, so we have already the weights. That's why we call it weighted average. So very simple math here. We're going to form a last column here by multiplying the midpoints by its own weight for each line here, and then in the end we make the summation. This summation will be representing the mean. It's interesting, right? So, and this in this case we call it not just mean, but we're going to call it as well as a weighted average. But we know from variance that if we want to calculate the variance, we need to get the difference between this point and the average. That means 0 minus 8.56, 3 minus 8.56, but we have to be very careful. And after we get the difference, we have to square it. And then after the square, we're going to multiply again by the weights in order to show that this is the weight of this difference. And then we take the summation. And after we get the summation, we can go ahead and calculate the variance and then the standard deviation. So this table gives you all what I just mentioned. So after we calculate the average here, based on the previous slide, then we're going to calculate the last column. Last column is, as you can see, the midpoint minus the mean, and the mean is 8.56, and the midpoint is this one here. So we get the difference and then square it and multiply by the weight, which is already given here, 23 in this case. The second one is 14, and so on. Once we finish all of them, then if we take the summation, this summation we call it variance. But once again, if they want to get the standard deviation, you need to square root this value, and it's a really very interesting. This is very small value, we think, but when we square root it, in fact, we get $10. So this is really impressive when it comes to math, to be honest. Okay, so those are the 5-number summary of the box plot. They are really very simple in Excel. You can really do it in Excel. So then we get the box plot, and I showed you the box plot already. Percentile, this is where you want to get percentile. If you don't want to get the 25th percent, this standard like 25th or 50 or 75, you want something like 80 percentile or maybe 60 percentile, then you can do this very simple math. Or what you need to do is this 80, because we need it, you multiply by number of points. You have number of points, and the points have to be arranged in ascending way, like what you see here. So on the upper side here we have the data, and then we sort it into ascending way. So we start with the minimum and end by maximum, and we keep every point in our case. So we have 12 points here, and if we want the 80th percentile, so we multiply 80 by 12, we get 9.6. So but we don't have a 9.6, so because this is between 9 and 10, right? So but it's 9.6 can be also seen as a 10, so 10 will be the position of the point that we need to get the 80th percentile. It's not the most accurate one, but at least it is 27 in this case. This is comparing groups could be through histogram and through also box plot. Also, I want you to read it. It's really easy to understand this slide, just to show you that there are multiple months here for New York for the daily volume in millions dollar in one of the years, and it was basically inside New York Stock Exchange. And you can see there are each month the data was collected in terms of daily volume, and based on this daily volume during this month, a box plot being represented for each month. So you can see if each month has its own box plot. If the box is high, large, like 12, month 12, it means there is really a high variation, which means a lot of people were selling and buying a lot. But when it comes to month number 3, the box is very small relatively, so it means the volume was not really high, which means people or the market was stagnant. There was no really much of work. Yeah, so here it's 12 and here it's the month 3. Dealing with outliers, as I discussed before, so probably I don't want to repeat myself. At this point, we have what we call standardizing the data. And as I told you before, standardization of the data, we need to use the z-score. So, and I showed you before z-score, but here I can show you the equation here. So z-score, it's, as I mentioned, you take your value. So if you have grades, if you want really to know what's the z-score of your value, so imagine you got 80 in your exam and the average is 70, so that means of the class, so 80 minus 70 is 10, and imagine the standard deviation is 2.5, so 10 divided by 2.5, the z-score will be in this case 4. So this is good, right? Because if I tell you that your grade is, I don't give you the 80, but I would tell you that your grade is the z-score of your grade is 4. So if I tell you it's 4, what is your grade? So immediately tell me, yeah, okay, I can know my grade if you give me the average of the class and the standard deviation, which is main. Really simple here. So all what you need to do, if you get the z-score, what is the y, or if you get the y, what's the z-score? So you have to be very flexible, and this comes a lot in the examinations. Sometimes I give you the z, and you need to get the y, or I give you the y, you have to get the z. Sometimes I give you the z and y, and I want you to figure out what's the average, or maybe what's the standard deviation. So try to be flexible, and this is okay. So let's yeah, sometimes data could be time series plot like that. It could be points, it could be lines, it could be both of them. It's very important methods we are not going to cover here in this course because it's really a little bit more complicated and advanced, so you have to go through another course probably. But it's very useful when it comes to analyzing any time varying behavior of systems like stock price or something. Last thing is what we call transformation. When the data is very skewed like that, and you have still a very long tail here in your data and very thin, so most of your data are focused or concentrated with very high density on the lower level, and hence you get very silly box plot like this one. As I mentioned, you can draw the box plot horizontal or vertical. In this case is horizontal, but you can see this point. This point means outliers. So if you have a lot of outliers like that, relatively a lot, then it disturb your data, as you see. So one of the ways to remedy the situation, we call it transformation. So the transformation could go with different methods. It's purely math. So you need to decide whether to use logarithmic function or square root function. Again, it depends on whether the data is skewed to the left or skewed to the right. In our case, it's skewed to the right, which means we have some data with very high scale, and the only way to make this high scale closer to each other, logarithmic function will be very useful. So now if we take our data and we take the log of our data, this what we see could be the result, which makes everything simple and easy. So I think I finish here. Try really, guys, to go through this handouts by yourself, read the slides carefully, because this will be the topic of next quiz. So good luck.